All right, in this second video of the last week, let me show you several examples about the Kuhn-Tucker condition. So let me start with the example, the first example where we try to maximize this function given this constraint. Okay, so the starting point is to set up the Lagrangian. So we set up the Lagrangian L. We first put the objective function, and using Lagrangian multiplier lambda, and open the bracket, we put in the constraint. So we first change the constraint to 300, so to this form, x1 minus 2x2. Okay? And by the first condition in Kuhn-Tucker theorem, the solution must be stationary point of the Lagrangian. So we take the derivative with respect to each choice variable and set it equal to 0. And with respect to x1, we obtain 2x1 times x2 minus lambda and set it equal to 0. And with respect to x2, we obtain x1 squared minus 2 lambda and set it equal to 0. Okay? And the second Kuhn-Tucker condition requires a constraint must be satisfied. Okay? And the third one, so no matter where we have a solution, complementary slankness condition must be satisfied. All right. So the third condition in Kuhn-Tucker theorem requires the second term of the Lagrangian. So this term is always equal to 0. All right. And then the way to solve this system of equations and inequality is we divide our analysis into two cases, depending on whether multiplier is positive or equal to 0. Alright, so case 1. Now suppose that lambda is equal to 0. Okay. And case 2, lambda is strictly positive. Right? If lambda is equal to 0, by this condition, we can immediately see that x1 is going to be 0. Right? And if we go back to the objective function, if x1 is equal to 0, the function boils down to 0. So should we regard this as a candidate for solution? If x1 is equal to 0, the function we want to maximize comes down to 0. Okay? That is clearly not a solution because if I choose 1 for each variable, okay, then objective function assumes 1. So I can easily make the objective function be larger than 0. Okay? So this is clearly not a candidate. So we rule out this first case. So lambda must be strictly positive. Okay? So we can immediately reach the second case. So if lambda is strictly positive, then by the third condition of Kuhn-Tucker, by complementary slankness, our constraint must be binding. So we must have a boundary solution. So 300 minus x1 minus 2x2 should be equal to 0 by kt3. Right? And now using kt1, so the stationary condition, because lambda is strictly positive. Right? So I can divide, so after rewriting this, 2x1, x2 equals lambda, and x1 squared equals 2 lambda. I can divide the first by the second. Okay? So if I take a ratio of each side, then on the left-hand side, I obtain 2x2 over x1. On the right, I have 1/2. Okay? In the first case, this was not possible because we have to divide it 0 by 0. That is undefined. Okay? But in the second case where we assume lambda is strictly positive, this job is well defined, right? So this job is doable. we can divide the first equation by the second. Right? And then so from this, we obtain x1 equals 4x2. Right? So now we complete two equations with respect to x1 and x2, so we can solve for each variable. So 300 equals 6x2. After substitution, then x2, we can get the value of x2, that is a 50, and x1 is going to be 200. Okay? So this pair satisfy all Kuhn-Tucker conditions with some positive lambda, and we don't have information about lambda because we are looking for the solution to this optimization. So what is optimal x1 and what is optimal x2? Okay, and it turns out that the unique candidate is going to be 250. Right? And even if we have more than one constraint, the same method can be used to find the candidates for a solution. Right? So we set up the Lagrangian x1, x2. Using multiplier lambda, we write the Lagrangian with respect to the first constraint, 100 minus x1 minus x2. And we need one more multiplier, mu, Lagrangian multiplier, because we have one more constraint here. Okay, so let me use another Greek letter mu. So this is called mu. Right? And then 30 minus x1. Okay. So it is quite a convention in economics to write the second Lagrangian multiplier with this Greek letter mu. Okay, I don't know why, but we usually denote by this green letter, the second Lagrangian multiplier. All right, then after setting up the Lagrangian, now we take the derivative with respect to each choice variable. And with respect to x1, we obtain first x2, and then we obtain minus lambda. Okay? And I have one more x1 here, so I obtain negative mu. Okay? And set it equal to 0. And with respect to x2, I obtain x1 from the first term, and minus 1 here. Okay? So with lambda, that becomes minus lambda. And the last term is independent of x2, so it goes away. Right? So after take the derivative, we set it equal to 0. All right, then we have two equations. Okay? And the second condition, simply requires x1 and x2 be smaller than or equal to 100, and the first choice variable x1 be smaller than or equal to 30. Okay, so this is the second condition in Kuhn-Tucker theorem, and we write down the complementary Slants condition. All right, so we have two complementary Slants conditions because we have two constraints. And the first condition requires lambda times 100 minus x1 and x1 minus x2 should be 0, no matter where we have a solution. So no matter no matter whether this constraint is binding or has slack, the product should be equal to 0. Okay, and then the same argument applies to the second constraint. So mu times 30 minus x1 should be 0, no matter whether this second constraint is binding or has slack. All right, then the way to solve this equation is, so now we have four possibilities, right? So in terms of Lagrangian multipliers, both Lagrangian multipliers may be equal to 0, or either one is positive and the other is equal to 0. or both of them are strictly positive. Okay. Now we examine case by case. So when lambda and mu both are equal to 0, then what happens? Then x1 and x2, both of them are equal to 0. Right? So this immediately brings us to x1 and x2 are equal to 0. Okay? From the first Kuhn-Tucker theorem, Kuhn-Tucker condition. Right? But going back to objective function, this is clearly not a solution. Right? If I choose 1 for 1 for x1 and x2 respectively, I can easily make the objective function be larger than 0. So we rule out this case. This case is ruled out. Okay. And the second, if lambda is positive, okay, and mu is equal to 0, then what happens? If mu is equal to 0, x2 equals lambda from this equation, and so does x1. x1 equals lambda. Okay. So we have x1, we have the same value of x1 and x2. All right? Then, if lambda is a positive, then by this complementary Slants condition, the expression in the bracket, so the first constraint must be binding. All right, so 100 minus x1 minus x2 should be equal to 0. But we have the same value of x1 and x2. Okay, so after substitution, we can easily find that each variable takes a value of 50. Okay, but it violates the second condition of a Kuhn-Tucker theorem. Although I didn't write down here, second condition requires these two constraints should be satisfied. But if we set x1 equal to 50, that clearly violates the second Kuhn-Tucker condition. So we rule out the second case as well. We can find the appropriate candidate for a solution in this case. Okay. Now lambda is equal to 0 and mu is strictly positive. Okay. Then from these two conditions, these two equations, we obtain that x1 is equal to 0 and x2 is equal to mu. Okay, x2 is equal to mu. All right, and that contradicts with this Slants condition. So if lambda is equal to 0, then x1, 0 is immediate from this equation, right? But if mu is strictly positive, by this complementary Slants, x1 should be equal to 30. Okay? But if x1 is equal to 0, there is no way to satisfy this Slants condition. Right? And due to this contradiction, this case is also excluded. Okay? So we are left with just the last case, lambda and mu, both are strictly positive. Okay, then what do we get? Now from this, we know x1 equals lambda, and from this equation, we know x2 equals lambda plus mu. All right, and because mu is larger than 0, so by this complementary Slants, we know x1 equals 30. Okay? So that tells us lambda is also 30. Okay, lambda equals 30. And we know lambda is also positive. So by this complementary Slants, x1 plus x2 should be 100. Right? So because lambda is 30, then mu has to be 20. So x2 must be 60. Okay? So we have a unique candidate for this solution that is a 30 and 60. Okay? So when we have more than one constraint, analysis becomes a little bit nasty because we have to check case by case depending on whether each Lagrange multiplier is strictly positive or not. Okay, so when we have three constraints, we're going to have three different multipliers so that we have a total 9 possible cases. Okay, so the problem becomes a little bit nasty, but this is a standard way to find the solution. All right. Now let me talk a little bit about minimization problem. So we just talked about maximization, but when you come up with a minimization, for example, now minimize f of x1 and x2 over x1 and x2. Okay, given this constraint, g of x1, x2 smaller than or equal to c. Okay. And for inequality constraint minimization problems, we use the same Lagrangian and the same Kuhn-Tucker conditions, but now we have to require multiplier lambda be non-negative or non-positive. Okay, so the sign of the multiplier is changed. Okay, but that is one just possible approach. The other approach is because if we have a maximization problem, so maximizing function f is equivalent to minimizing negative of this function. All right. So we can write the Lagrangian just by putting negative sign in front of the objective function when we encounter minimization problem. That is the second approach. And the third approach, which I personally like, is put just a simply negative sign in front of the multiplier. Okay, so change this plus lambda, just change this plus lambda to minus lambda. Okay, then we can still use the same Lagrangian except this difference. All right, and then the sign of the multiplier remains positive in both maximization problem and the minimization problem. Okay, so we have three different but equivalent approaches. You may assume the multiplier be non-positive, okay, in case of a minimization problem, or you can just put the negative sign in front of the objective function, okay, because a minimizing negative f is equivalent to maximizing original function f. Okay, then you can solve the given minimization problem, or you can change the sign of the multiplier. So this plus sign, okay, in the maximization problem to minus. Okay, and one advantage of this last approach is now you don't have to worry about the sign of the multiplier. The multiplier remains positive in both problems. Okay. All right, so now using that, let me tackle this example. So although we have two constraints, let me erase this one, okay? Just with this say a single constraint, let me solve out this minimization problem. Right? Then all right, and we set up the Lagrangian. So x1 minus 4 squared plus x2 minus 4 squared, okay, the same term. But now in front of lambda, we put the minus sign. Okay, and just ignore this constraint for a second. We pay attention to this constraint. So 12 minus 3x1 minus 2x2. All right. So the way to write down Lagrangian is the same as before, exactly same as before, except this minus sign. Okay, we change the constraint to the form something is larger than or equal to 0, like this one. Okay, and we use the same objective function. We don't have to minus sign here. Put the minus sign here. Okay, the only difference is plus lambda now becomes minus lambda. I think this is the easiest way to solve a minimization problem. So I usually adopt this last approach. I usually take this last approach to solving a minimization problem. If you have different opinions, then you may take the first or second approach, whatever you want, okay? All right, then we find the stationary point. Then with respect to x1, we obtain 2 x1 minus 4 and plus 3 lambda and set it equal to 0. With respect to x2, 2 x2 minus 4 plus 2 lambda and set it equal to 0. And the second Kuhn-Tucker condition is this constraint. This constraint should be satisfied. And the last one is complementary slackness. So lambda times 12 minus 3x1 minus 2x2 should be equal to 0. Okay? And then once again, we divide our analysis into two cases. Case 1, lambda is strictly positive. Lambda is equal to 0. All right, so if lambda is 0, then from these two equations, you can immediately see that x1 and x2 both are equal to 4. If lambda is 0, okay, x1 has to be 4 to satisfy this equation, and so is x2. x2 should be equal to 4. All right, but if both x1 and x2 are equal to 4, going back to the second condition, now we have to check whether this constraint is satisfied. Now 12 plus 8, that does exceed 12. Okay, so that constraint will be violated, right? So case 1, we rule out the case 1. Okay. Now case 2, lambda is strictly positive. Okay, and by the complementary slackness, we have 3x1 plus 2x2 should be 12. Okay, so we must have a boundary solution. Okay, then let me first solve this equation. The very first condition for x1, then x1 is going to be 4 minus 3 lambda over 2. No. Okay, solving for x1, I obtain 4 minus 3 lambda over 2. And solving this second equation for x2, I get 4 minus lambda. Right? And then substitute this, alternative form for x1 and x2. Then that gives me equation of lambda only. All right. So now you can solve this equation for lambda. Okay. So I have minus 9 lambda over 2 minus 2 lambda. So that should be negative 8. Okay. So changing the sign to positive, then 2, so 13 lambda over 2 equals 8. So I guess lambda is 16 over 13. Oh, that is a little bit nasty, but so as soon as we get the value of lambda, then we can substitute lambda here to find the value of x1 and x2. Okay, so let me leave the exercise. So let me leave the remaining job for exercise. I think that is just a simple algebra. So I believe you can do that by yourself. All right. Then I explained the Kuhn-Tucker condition, but remember, Kuhn-Tucker condition just gives us a first order condition, necessary condition for a solution. Okay, so we start with this presumption that x1 star and x2 star is a solution, and the solution must satisfy these three different conditions. Okay, so it gives us just a candidate, and how do we find the real solution? Okay. Now, we are going to study sufficiency theorem, and that is very similar to the previous one. Okay, so if Lagrangian is quasi-concave, globally quasi-concave with respect to x1 and x2, then the first of the condition becomes a sufficient condition in case of maximization problem. Right? So if, Lagrangian is quasi-concave, globally quasi-concave with respect to x1 and x2, then previous first order condition, so the Kuhn-Tucker condition becomes a sufficient condition. All right? And if the Lagrangian is quasi-convex with respect to x1 and x2, then the previous Kuhn-Tucker condition becomes a sufficient condition in case of minimization problem. Right? So to summarize, if we have a constraint maximization problem, okay, the standard maximization problem, and suppose that f is quasi-concave. So this is quasi-concave. So this is quasi-concave, and this is quasi-convex, Cx, right? Then because lambda is non-negative, and if this function g is quasi-convex, its negative becomes quasi-concave. Okay? So the Lagrangian is just a sum of two quasi-concave functions that is quasi-concave. Right? So in this case, if x1 star and x2 star satisfy the all Kuhn-Tucker conditions, then it's going to be solution to constraint maximization problem. Okay? And so remember, linear constraint. So linear function is both quasi-convex and quasi-concave, right? So whenever we have a linear constraint, we don't have to check this one, okay? Function g is automatically quasi-convex, right? So it's enough to check the objective function is quasi-concave or not. If that is a quasi-concave, and we attempt to solve a maximization problem, then the Kuhn-Tucker condition becomes sufficient condition. So if we find a candidate satisfying the Kuhn-Tucker condition, that is going to be solution, right? So going back to this example, say this example, we attempted to maximize this quantity, right? Given the linear constraint, and remember, Cobb-Douglas is quasi-concave, okay? Quasi-concave. So this candidate that we derived from the Kuhn-Tucker condition, so that should be just a candidate, right? Because Kuhn-Tucker condition just is necessary condition. But whenever objective function is quasi-concave and given constraint is linear, so it's a linear x1 plus 2x2, that is automatically quasi-convex and quasi-concave. So we don't have to worry about the constraint, right? So as long as the objective function is quasi-concave, this candidate is immediately solution to this maximization problem. Okay. All right, so using that, let me do one more example. So that is a utility maximization problem. Okay, so now we have a different objective function. Now the basic constraint takes a very general form, but remember this is a linear function. Now we want to maximize this function over x and y, and with respect to x and y, px, that is a price of a good x, that is a constant, and py, price of a good y, that is also constant. So the constraint is given by a linear form, right? So, and the objective function is quasi-concave, because that is a Cobb-Douglas form, x to the power alpha and y to the power beta. No matter what, this alpha and beta is quasi-concave, right? So we can set up the Lagrangian and finding Kuhn-Tucker conditions, and we can first derive this candidate for a solution to this maximization, and that candidate becomes a solution because it satisfies these two conditions: quasi-concavity of the objective function and quasi-convexity of the constraint. Okay, so the Kuhn-Tucker condition becomes a sufficient condition. All right, and in case of minimization problem, so we now want to minimize function f given this constraint. Okay, then associated Lagrangian is L f of x1 comma x2 minus lambda c minus g of x1 and x2. Okay, and in case of a minimization problem, if the Lagrangian, so this whole expression is globally quasi-convex, if L is quasi-convex QCX, okay, then the the candidate, so the candidate obtained from the Kuhn-Tucker condition is going to be solution to this minimization problem. In case of quasi-convex, we have this form. So where the derivative is equal to 0, we have global minimization. We have a global minimum, right? So the first of the condition becomes sufficient condition in case of quasi-convex Lagrangian. Okay, so now we have to check under which condition Lagrangian becomes quasi-convex. If this subjective function is quasi-convex, and we have two minus sign in front of g, right? In front of g, c minus g, lambda g, x1 and x2. Oh, I think it should be, sorry, this is a typo. It should be quasi-convex as well. Quasi-convex. Quasi-convex. Yeah, that's right. So whenever we have this kind of a constraint, all right, and then the sign of the multiplier is still positive because I already put the negative sign in front. So it's going to be plus lambda times g, right? So if g function is quasi-convex, then linear combination of quasi-convex functions is quasi-convex. So only under these two conditions, I can make sure Lagrangian is also quasi-convex, right? So the function, objective function must be quasi-convex, and function g must be quasi-convex too. And in this case, Kuhn-Tucker condition becomes a sufficient condition, right? Because we have two negative signs, so it comes down to just lambda plus lambda on g of x1 and x2. But if the given constraint was, if the given inequality was reversed like this, okay, then we are gonna have g x1 and x2 minus c inside this bracket. Right? In this case, if g function required to be larger than or equal to c, then function g must be quasi-concave, because now we have a negative sign in front, right? So for in order to make this Lagrangian be globally convex, quasi-convex, function g must be quasi-concave. All right. Okay. So all right. So now, if we think about this expenditure minimization problem, so consumer wants to figure out the cheapest way to attain her target utility U bar. Then the associated Lagrangian can be written as L pxx pyy now minus lambda x to the power fourth y minus target utility u bar. Right? And this is called expenditure minimization problem in microeconomics. So now, there is a one target utility the consumer wants to attain. So given this utility function, now the consumer wants to find out pair of x and y. And in order to reach this target utility, what is the cheapest way? So what is the pair of x and so what are the pair of x and y? The minimizing expenditure, okay? And at the same time, for reaching this target utility. And this is called the expenditure minimization problem. And the associated Lagrangian can be written this way, okay? And now the objective function is linear, okay? So it is quasi-convex, right? And then this function, Cobb-Douglas, that is quasi-concave. This is quasi-concave. But we have minus sign in front, so minus lambda x to the power fourth y. This is going to be quasi-convex. Okay, so now we can make sure every function inside this Lagrangian quasi-convex. So Lagrangian becomes quasi-convex. Okay, so the Kuhn-Tucker condition becomes a sufficient condition. All right, so let me finish this lecture video by solving this minimization problem. Let me just solve one problem here. All right, so now we have L, Lagrangian L is pxx pyy minus lambda minus target utility u bar. All right, and then by taking derivative with respect to x, I obtain px minus lambda x to the power fourth becomes 4x cubed times y, set it equal to 0. And with respect to y, now pxx is a constant, pyy becomes p sub y. Okay? And remember, this is not a variable. Px and py are constant, given price. So given price of good x and good y, what is the cheapest day? What is the least cost? So which consumption bundle gives us a least cost in order to achieve this target utility? Okay? So if we take the derivative of this p sub y times y, treating p sub y as a constant, we are just left with p sub y. Okay, and now x to the power fourth y becomes just x to the power fourth. So we have this one. All right, and then the second condition requires the bundle x and y should give us the target utility and list. Okay, so the constraint must be satisfied. And the third condition requires the complementary slankness. All right, and then now we divide our analysis into two. When lambda is equal to 0, what happens to these two equations when lambda is equal to 0? Then px is going to be 0, py is going to be 0. Okay, but px is not a choice variable. That is an exogenous variable. That is the price of good. But price is determined by competition in the market. All right, so we obtain px is equal to 0 and py also equal to 0. That is not possible, right? That is not possible. So unless px and py, so good x and good y are free, we can solve this minimization problem. with this zero multiplier. Okay, so we learn out this first case. So now case 2, lambda is positive. Okay, so if lambda is positive by the complementary Slants condition, the constraint must be binding. And now lambda is positive, so let me rewrite these two equations into Px equals lambda. So for lambda x cubed y, okay? If I rewrite this first equation, then I obtain this one. And p sub y equals lambda x to the power 4th. All right? So if we take the ratio, then we obtain p sub x or p sub y, and lambda will be cancelled, right? And x cubed by cancelled by x cubed on the bottom, and I have one more x on the bottom, and on the top I have 4 times y. Okay, so that comes down to solving for x, then x is going to be relative price px over py times 4y. Okay, and then substituting this to this binding constraint, then I'm gonna obtain one equation. So equation for y, so px py to the power 4th and 4 to the power 4th, y to the power 4th, and times y. That is u bar, target utility. So solving for y, I obtain y to the power 4th is p so p y over px yeah, I'm sorry, this is a typo. It should be not px. When we solve for x, I obtain py over px, py over p sub x. And so it should be p sub y over p sub x. P sub y over p sub x. Okay. And 4 to the power 4th. So it should be divided by yes. It should be p sub x over p sub y. All right, and then 4 to the power negative 4, and then u bar. All right, I just moved these two terms to the right hand side by dividing both sides by these two factors. Okay, so this is going to be its reciprocal, and for the this is also we should take the reciprocal. So this guy becomes 4 to the power negative 4, right? Then consequently y. This is a little bit nasty, but now take the power, so raise it to the power 1 over 5, and I obtain this. Okay? So this is called Hicksian demand in economics. Hicksian demand for good y. So it tells us given price, in order to achieve this target utility U, how many units of good Y does this consumer have to consume? Okay, and now you obtain Y, and you can easily obtain X from this equation. Okay, this equation. But I'm not gonna solve that, right? Because this problem is too nasty. But I just wanted to introduce the another concept of a demand function that is derived from this expenditure minimization problem. Okay, but let me just focus on method. All right. So even if we come up with a expenditure minimization problem, we can use the Kuhn-Tucker condition and the same Lagrangian, except this negative sign. Uh, we can derive the optimal solution. Then the optimal solution is referred to as the Hicksian demand in economics. All right. So I have just one more example, but let me do this in the review session, or in in the review session. Okay. So let me stop the last video here, and just as a final short remark, I really thank you for your all effort and all time you put into you put into for this class, and wish you good luck wish you good luck with the final exam. And I'm gonna hold one more review session next Friday. And I'm sorry for late upload of this video. So you know what, the final exam, so I will adjust the level of difficulty, of course, and then I already collected your opinions about the final exam, and so I'm trying to reflect those opinions into the final exam. Okay. So I went through the final topic a little bit fast. It is Kuhn-Tucker condition, but don't worry about that. We're gonna have 2 hours in the review session. I'm going to go over some exam. I'm gonna show you some more examples in the review to help you understand this Kuhn-Tucker. Right? Once again, thank you for your time and effort you put it into for this course. Right? And wish you good luck with the exam.